let's use the wave function operators to create multiple particles. So I'm going to tell you that. Let's try. Let's try to just use a product of two wave function operators. Try this product first. And let's see how this acts on a two-particle state. So the two-particle state in the Fock representation, we'll write as for fermions. So maybe we have one in the m state and one in the n state. So this is the state m and n, right? Okay. Now remember the part because of these commutation relations. Because of these commutation relations, the order that I place R1 and R2, that I place these two operators, and the order that I place these are going to matter. Okay? So what we're going to get is we're going to see that at R1 you're going to have the m, maybe at R2 you're going to have n. So the order matters here. So let's see what happens. Writing everything out. Now we need to use two other summation indices. Maybe we can use n1 and n2. So let's be careful to respect the order of the operators. And so this one comes in first, right, because we place R1 in front, attached to its wave function. Then there's this one. Okay. So let's move these things around. So this is summation n1 and n2, the product of these wave functions. Okay. And what's important is there's four terms here. So we're going to just use commutation relation again. So when an annihilation operator sees a creation operator, we change it using the commutation relation. This goes to the identity delta n2 and minus their order switch. Correct? Okay. So now this is going to help us remove one of these. Okay. So let's consider the first term. So sigma n1, n2. And let's forget about the r. Oh, wait, we can't. There's R1 and R2. Okay. So we're going to have a, well, the identity operator can be dropped. Okay. We're going to have a delta n2m. Okay. And then the big n1 is I'm going to see this. And the average. So this is coming from this term. Okay. And now let's think about this term. Okay. This term we have a minus sign. Okay. There's no delta functions, but now the order of the operators have changed, and conveniently, every creation operator is right next to another annihilation operator. Correct? Okay. So, go what? Oh, sorry, yeah, this one. So now this is the result so far. Okay. Now we're going to use this to remove the summation over N2, right? And also you can think over here I'm just going to do the same thing, right? I replace this with a delta function of N1 and N, and then the other term, the annihilation operator sees the vacuum directly, so I can drop it. So, and then that delta function is going to remove the N1 summation. So, the next step, the first term becomes phi of M or R2 phi of N R1, correct? Because the two delta functions associated with this term is delta N2M and delta N1N. So these things become this. Okay. Now the second term, what I can do is
shouldn't BM bottom to BM dagger?
no. Okay. Sorry. Yeah, of course. Okay. So now the second term there. Okay. Let's work with this product. So this is going to be subtracting something. So I can change this product. Okay. This two is going to give me a delta N1, delta N1 M. This two is going to give me a delta N2 and all the other terms. For all the other terms, I have this thing seeing directly the zero state, the vacuum state. So I can drop all the other terms. Right? Okay. So basically, the other one is just going to be a minus sign and with their indices switched. Okay. So this is phi n R2 minus phi m R1. Okay. So now you notice that this is correctly symmetrized, anti-symmetrized. So if I switch the label of 1 and 2, I acquire a minus sign. Right? Okay. There's just one problem with this. What is that? This wave function is not valid right now. What's the problem with this wave function? Yeah, it's not normalized, right? And also we need to attach the vacuum state. So to correctly normalize this, it needs a factor of 1 over square root of 2, right? Okay. So we get that starting with this state. Okay. So if I use the vacuum state, 1 over square root of 2 sine R1 sine R2 and this is going to give me the correctly normalized, correctly anti-symmetrized two-particle wave function. Right? Okay. So now we can again. Let's do this. Let's do what we did for the similarly for the one for this case. And deduce what's the action of this creation operators. So we take the Hermitian conjugate of this, which we can conclude that phi dagger of R1, R2. Now we should be careful because of the order of things. Let's take the adjoints of this. So the state Mn appears here. And then over here we have 1 over square root of 2 doesn't change. These two operators need to switch their order, right? measure R2 measure R1 0. And we know that this is going to be this conjugate. Right? So then we can conclude that the operator this thing, creates the state, R2, R1. Okay, it creates a two-particle state. Okay. And you need to be careful with R2 and R1 or R1, R2 because in the end it amounts to a minus sign in the wave function. Okay. So the generalization to an n-particle case is very simple. We just multiply n copies of these wave function operators and then attach 1 over square root of n factorial. Because that's the usual factor that comes in when we normalize these Slater determinants. Right? So 1 over square root of n factorial phi of R1 and let's define this to be psi, a total wave function operator psi n of R1, R2, R3, etc., R3, and the action of this is that, okay, suppose I define the psi, the phi, okay, of R1, R2, R3, and to be the correctly normalized and correctly anti-symmetrized wave function of n particles that we were familiar from ordinary quantum mechanics without second quantization. Okay. So this is that wave function. So how do we get this wave function? Well, the thing is we use the vacuum state. And operate this on a state with R1. Okay, so this is equal to this. Okay. Are there any questions? Let's check if we have made a sign error or not by using the two-particle case. So in the two-particle case, the way we've written this is psi 2, okay, of R1, R2. This is equal to the product of psi of R1, psi of R2. Right? Okay. And over here, we have computed this explicitly. R1, R2 operating on M and N is going to give me M with R2, N with R1. Okay, so when this thing operates here, I should get the M is the state for R2, right? And the N is the state for R1. Okay, so we have actually made a mistake here. So this should be Rn, Rn minus 1, R1. Okay. And the reason for this should be clear, right? Because we have said that we require when the wave function operator sees something, we require that thing to be at the first position before we can annihilate it. Right? So when I write a product like this, and this appears at the last position, so this sees the state first. Right? So so within the state, you need the Rn to be in the front. Right? So this is correct. Okay. So this is the n particle generalization of this n. And without actually computing this, which is very tedious when n gets large, because you need to anti-symmetrize all of them, and you need to go over all of the possible permutations. Okay, we can just use this. Okay, which all you need to do is really take care of the order of these operators, and then also attach this overall normalization factor. And then the mechanics is completely described when we, the information in the wave function is completely written when we just write this. Okay, so this is a really, really simplified notation. And the advantage of it comes whenever the particle number goes up. Okay. Any questions? No? Okay, so now let's think about a hard problem. So far we've only been working with states. How do we construct operators? Operators like, because to do quantum mechanics, to do many body quantum mechanics, so far we've only introduced a bunch of notation. How do we write our operators in this new representation? Operators such as the Hamiltonian, the kinetic energy, the total kinetic energy of n particles, the potential energy of interacting particles, and all that. So how do we write down operator? So first, let's recall that number operator thing. Okay. So we wrote the total number operator to be summation over I to be this form. Okay. So I can define its components. So the operator that counts the number of particles in the ith state. Now this is just one component. Correct? Okay. So now I can think about a one particle operator. One particle operator meaning that the observable is associated with one particle. I'm considering things like kinetic energy or momentum of single particles. I'm not thinking about interaction energy of pairwise particle pairs. So let's call an operator like this by the notation A1. Okay, so it's a one particle operator. And let's suppose that on these bases, on the basis that we have chosen to write the wave function operators in. Okay, so remember the wave function operators are I'm going to use the A1 over here, this operator, this observable, has eigenstates n. So in conventional quantum mechanics, the way we would represent it is by its eigenvalues is diagonal in this representation. And the representation is eigenvalues multiplied with this. Correct? So now, let's think about what this changes to in the new representation of Fock states. And the way we did this in conventional quantum mechanics is if we have a one particle state, it's simple. Right? So if our particle was in the M state, right? And we wanted to think about the matrix element like this, right? What would we do? We simply compute the M and N are going to see each other, so this is just going to be A1M, right? Okay, of course, you can also put in a one particle state with a superposition of eigenstates. So particle need not be in an eigenstate. And we can still work with this, but then you get a summation of the possible eigenvalues. So that's how what we did in the ordinary quantum mechanics. How do we do this in when the states are written in Fock states? Okay. So basically, we're asking what happens when I have a Fock state like this? Let me write N1 prime, N2 prime, etc. And big N prime. Okay. So we have a total of N particles. Right? And then this particle, this operator acting. The matrix element here. Okay. And then this is N1, N2, etc. And big N. Okay. So what does this do? Now let's plug in this representation into there. Okay. Remember that when I write something like this is a direct product space. Okay. So this is really N1, N2, N3, N3, right? Right? Okay. So now if I project this onto a subspace spanned by a one particle state, okay, this is just going to detect whether that one particle is present, that one state is present in this list. Right? So this is going to check if n it belongs to this this bad notation. Okay. Whether m okay belongs to the these n's, okay, n I, right? That's what happens when I try to project this state onto the this was m over here. Right? So what I mean is, let me write this in terms of A1m like this. Okay. Now also, it's going to do the same thing on this side, right? It's going to check if m belongs to this list of states. Right? So now using the orthogonality of the states, okay, I can turn this expression, okay, I can turn it into this because I'm summing over all of the possible states, and so all of them are going to be picked up by sum, right? Because I'm summing over all of the possible states. So I can change this into A1m, okay, and then A1 okay. Now what do we mean here? This might be a bit confusing to you. Let's think about a specific case. Okay. So suppose I had so on this side, suppose I had the state K, L, M, and N. On this side, I have the state Q, L, M, N. Okay. What is this inner product? 0. Okay. So what you need is for the two to completely match each other. So what this tells you is that in this new representation, this thing is still some kind of a diagonal thing. Right? Okay. Now, remember we have a factor of 1 here. Okay. And for fermions, this is convenient because I can turn this 1 into the number operator. Right? That counts the number the state in the let me turn this into so this is equal to b dash m b m, okay, which is the operator that counts the number of particles in the m state. Okay. So now this is right now over here what appears is this eigenvalue. I can turn this inside, right? Because this is guaranteed to be an eigenvector of it for some n, okay? And I'm only summing over those things. Okay? So I can turn this into sigma m a1 m n1 prime n2 prime n3 prime. Okay. Then m. Now this is convenient. This basically captures what we just said. Okay. First of all, we're going to see whether this term contributes to the sum by seeing if the M state is within this list. So I can do that alternatively by counting the number of particles in the M state, and for fermions that is 1 or 0, by using this number operator, right? Okay, and then I'm going to check if the two states are the same. Okay. So now I can write this as moving these things inside. And this is B M dagger. Correct. Okay. So now, because we've started with arbitrary states in the Fock representation, it must be that the matrix element of this A operator, the one particle operator, in the Fock space representation is simply equal to summation over M. Yeah, M A. So actually make some kind of notation. So let me say that this is the A1 operator represented in the Fock space. Okay, when the states are in the Fock space. Okay. So this is this. No, but this is the original operator in conventional quantum mechanics. Right? So to go from the operator in the conventional quantum mechanics to the operator in the Fock space, we do this. And this is for a Fock state that's written with the wave function operators using the eigenstates of this original operator. Okay. So now let's just think about this from a intuitive manner. Okay. So basically, when we have some kind of an operator here, okay, it's just going to check if the M state is occupied, and if it is occupied, it's going to register its eigenvalue, right? So this is quite intuitive. Okay. Right, so these are one particle states. And what are the examples of one particle operators? One particle operators. The kinetic energy. So I can have the Hamiltonian of a bunch of free particles. Okay. Free particles in the sense that the particles don't interact, okay, but they could move in the presence of an external potential. Okay. So the Hamiltonian could be in conventional quantum mechanics. The one particle Hamiltonian is what? Is the minus h bar squared over 2m. This was the conventional one particle Hamiltonian. Now, if I have a bunch of particles, then naturally I just sum over their one particle Hamiltonians because energy is an additive quantity. H I minus. I from 1 to n. Okay, and let me label this new Hamiltonian by 1 n. Right. So what we have done so far is we have said that this Hamiltonian, when written in the Fock space representation, it can be written as just think about if I wanted to count the total energy of all of the particles, all of the n particles. then it will make sense to me because I basically detect what are the M states that are occupied. And then if I count one, I write down its energy item. So this is the one particle operator. One particle operators are still pretty simple. And you can just understand this intuitively. Now let's move on to two particle operators, which are a bit more complicated. But again, with our formalism, they're quite easy to write down. So for two particle operators, we can think about an operator describing the interaction between two particles at position R1 and R2. So this would be a function that's dependent on R1 and R2, correct? Okay. So this would describe a pairwise interaction. Now, we're going to only think about the symmetric ones, where B of R1 and B of R2 is equal to this switch. Okay. And this is true for most pairwise interactions. So basically, the interaction energy of this particle to this particle is the same as to this particle to this particle. Okay. So think about how we did this in conventional quantum mechanics. Now, in conventional quantum mechanics, we work with a really cumbersome state, which is we work with wave functions that were correctly normalized and anti-symmetrized. Now, these wave functions can be represented by L1, R1, R2, R3, all the way to Rn. Right? It can be represented by a state like this, and a state like this, we mean that. What do we mean by this? We mean we've created a particle at R1, created a particle at R2, etc., etc. Okay. So this, when written in terms of the Fock space representation, this is given by 1 over square root of n factorial. I just write this out in terms of creating something from the vacuum state. Right? So notice that this appears at the rightmost position. So this was the one that's first created, right? And this one is the one that's created last. Okay? So the correct order of these creation operators are this. So I just write the order like as usual. So this is our new state. We have chosen, in the Fock representation, these two are the same. But in conventional quantum mechanics, this is the state that corresponds to the really cumbersome wave function. Right? Okay. But now, if we think about the action of the two-particle pairwise interaction back in conventional quantum mechanics, we will write something like this. So we have operator V acting on a state like this. R1, R2, R3, So this is going to pick out. It's going to pick out two of these coordinates to fill these two slots. Okay. Maybe I shouldn't use R1, R2. Let me use R and R5. So we can see. I'm going to pick out two of these coordinates to fill these two positions. Okay, and then OM requires that they're not the same. Okay, because this is a pairwise interaction. So this can be one way I can write this is perhaps sigma n from 1 to big N, but n is less than m. Okay, so follow me here. B of R n and R m. Okay. R1, R2, R3. why do we write this n less than n? This is just to avoid overcounting of things twice. I can do this, or I can count things twice and divide by 2. Just requesting that n is not equal to n. So this is equal to 1/2. Okay, summation over all the possible n not equal to n up to big N v of r n Correct? Okay, so this was what was done in conventional quantum mechanics. So let's see how we can do this in the second quantized form. And instead of deriving the thing, I'm going to give you an expression, and let's check if it works. Deriving the thing, if you read the lecture notes, there's a way to do this by thinking about a singularity transform. Okay, but it's considerably more complicated. Okay, but once you, these formulas you only need to derive once. Okay. So I'm going to tell you that in the second quantized form, this goes to 1/2. Okay, integral over dr, integral over dr prime, and right dagger of r. Okay, so now what we're going to do is use this, operate on